Okay, let's proceed to the second step. We defined the sensor and we created a lookup table, and now we want to check out if everything is defined properly. For this, I need to import my dataset completely, so I also need all the metadata. I can close the resolute. So for high-specs data, importing the data goes through this parch status. So I'm importing the status with the GCS file first. That's that one. And no time found in here, but the time will be readily available from the NV header. So I'm selecting the input image cube, which is that one. And the digital elevation model has also to be selected. That's this one. And now it seems to be everything all right down here. One could check if the time has been taken properly by checking the NV header. So I can show the NV file, this one, and if I'm looking at the NV header, it tells me about the time, acquisition time, which is correct. So now this is everything all right. So the sensor is the one we have defined before. That's the high-specs veneer 186, and the date is okay. This data has been taken from the GCS file from Parch. So now I can write the in file, and it will create a new one. The in file, INN file, is the parameter file for Atcor, which is used later for the processing. So it contains all necessary parameters to do the atmospheric correction. Now the next step will be to run Atcor, or have a preview of the atmospheric correction. So I go into Atcor 4. I'm selecting the input image. Only if selecting the input image, all parameters will also be written from the in file. So it found the scan angle file, so there is already an output. That's why I have to choose override. And I can check if the flight parameters are correct. Seems to be okay. It was flying at 1.5 kilometers above ground, and everything is fine. The selected sensor is the one we have chosen before, and this calibration file containing the scaling factor seems also to be correct. Here I don't change anything for now, and I only want to check the spectra. So I go into the spectra tool. I don't change anything here. It seems to be appropriate. It's in the 820 spectral band. One could click a little bit in here to update the band numbers, but in principle this won't make a big change. So that's something I don't need now. And finally I can display the spectra, which are just by clicking in here. Looks at first glance looks quite okay. I'm increasing the maximum of the reflectance. Is okay as well here for most cases. So here you get some vegetation. What makes me puzzled is that I had 100% reflectance up here. That's something which is not very common, but for other targets everything looks all right. So that it seems to be some specular reflectance in vegetation, or some some unknown effect for now. So this looks all right. I also can check for the preferences. So edit preferences is here, and see what has been said. Most important part is the setting of the interpolation. So currently the 760 nanometer band is interpolated. I'm switching this off now to see what happens. The 940 could also be switched off, and the 825 is used for the water vapor retrieval anyhow. Down here I usually don't change anything, so maybe for the interpolation ranges one could change if you have artifacts at the edges of the absorption bands. So I'm saving the parameters. I can do another preview now because the presets have been updated. So I'm going back here and have another look at the outputs. And now what you see is a certain difference in the reflectance. So there are no interpolations left, and there is this Z shape in the 760 band. This Z shape is usually the case if you got spectral shifts. So there must be some spectral shift in the data. And the only thing to do to check out the spectral shift is to go into the spectral smile detection. So I go over here, check out if the smile is okay. I have my subset. Everything is already predefined. I don't need to change a lot. I'm only giving here a parameter file to save all the outputs, and can run this one. This will show me if the spectral calibration is okay or not. So it's also a step which is only be done once in the beginning if you start learning about your sensor. Later you may need this only if you have questions about the calibration accuracy or potential degradations of your system. So I'm going to run it, and it will average all the spectral bands, and then it will detect the smile based on atmospheric absorption features. So it goes through about 5 or 6 features in the visible near infrared. Obviously the others can't be used with these sensors, so the ones in the shortwave infrared. And now that we have seen this processing, we get a data set containing spectral shifts, which can be checked out. Like that. I accidentally pushed the same button again. And I'm going to wait a second to let it complete. Here you are. So I'm going to plot it now, and you see the smile at various positions. If you go through you take the big arrows, then you see how far the positions are off against reality. So it's in a range of maybe 1 nanometer. What you see here, accuracy is maybe a little bit too low. I should have taken maybe 0.02 nanometer instead of 0.05, because this is a very narrow band sensor, and so the accuracy is slightly reduced. But anyhow, now that you have this information, you can update your sensor. So you apply a spectral shift to your sensor, and this will create, so you have your input sensor, that's your current sensor, you have the smile data, which is the spectral shift data as well, and you can create your output sensor, which may be that one, and now you could apply the smile, and a new sensor is created with the shifted spectral positions. Whenever you update the shifts, you also have to update the atmospheric database. So you have to go back to Resolute and select the shifted sensor now, and like this. So it would be the shifted, that one. And now you could choose your flight altitudes again. So maybe from we had between 1000 and 3000. Go back, and now you could run it. I already ran it, so I don't do it now. So that's for the updated sensor. And for the processing, you can go back to the Atcor F, select your sensor, input image, sorry, and then you have to select your sensor, and now you got a new sensor, so you have to switch to the shifted one, to that one. Okay, done. And it complains about the atmosphere, so I have to select again because it was a new sensor. Now the atmosphere is selected. If we have been flying at 1.5 kilometers, one has to choose the atmosphere just close by. So the 1000 or 2000, it will be interpolated to the correct position anyhow later. I can choose the spectra tool again. Click in here and I'll get similar results as before, but now with no set shape, but still some more correction here. That's a different story. I won't go into. It's related to the full FF max of the sensor. So I'm because I have still some problems in the 760 band, I switch on the interpolation at 760 like that in the preferences, and now I can go to the processing of the data. For the visibility, I don't do much changes. One could do a visibility estimate. Maybe I'm going to do this. It says you should go very high. One has to be careful for high resolution data with high visibilities. Maybe visibility of 80 would be fine in this case. It's 110 is not realistic. The visibility estimator is not very accurate, I must say, for very high resolution data because of the shadows which are causing troubles there. Now I'm going to do an override and do the image processing. I don't choose variable visibility due to the just mentioned problems with aerosols, and I do the variable water vapor. That's okay. For the water vapor bands, it's also fine. I can run the atmospheric correction, and I won't go further higher with the visibility, and now it will go through all the bands. And for the flat processing, so without digital elevation model, this is quite fast. So in the end, you have it in a few seconds even. So that was the processing. Let's have a look at the data, at the output data, which is that one. And have a look at the spectra. And the spectra looks mostly nice, but there are some questions about the spectra. One is the very high reflectances in certain cases. So 80%, that's not typical, but on the other hand, sand looks very realistic, but there's quite some noise in there. So this spectral noise needs to be accounted for, and this can be accounted for by a further step, by a polishing step. So polishing, you go to the spectral polishing. Usually one chooses the statistical filter, and the Savitsky-Golay is the most accepted one. For high resolution systems, I would take a factor of 4 and create a polished output Savitsky-Golay SG. Okay, and this will create a polished image cube, which is also quite a fast process. And let's have a look how this spectral look like. So that's the SG, S-Goal, yeah. Spatially you won't see a difference. And from the data, there are some artifacts left. Well, it's on 20%, that's why you see a lot. One could go here and do a reset range. Then one can see better what happened to the spectra. We have problems above 900 nanometers, so this is a water vapor range, and this could be improved by better spectral full FF max calibration, something which would have to be evaluated, but in principle the atmospheric correction works as expected. So that's it for the standard processing, and I think at this point I'm gonna interrupt.